This is the second to last full exam I have to go through for MA 265, and let's get going. This is spring 2017. We're doing the whole thing. Question 1, let m and n be greater than or equal to 1 such that m is greater than n. So if we're drawing that out as a matrix, if we have A is m by n, m greater than n will be a matrix that is taller than it is wide. So if we represent that with a transformation, we'll be going from some lower dimension to some higher dimension. That's something to keep in mind as we read through these answer choices. 1, a linear system of m equations in n variables, so that's what we have up here, is always consistent. Is that true? Well, let's take a look at a small case. Let's choose m equals 2, n equals 1. So we have two equations in one variable. What if we have x is equal to 1 and x is equal to 2? That is one equation, two variables, and it's not consistent. So 1 is not true. What about 2? A linear system of n equations in m variables is always consistent. So that is like saying, let's see. Let's go with this. And I kind of messed up by using x there. Really, there should have been some constants outside of it, because if we write let's see, a 1 equation using two variables, c1 x1 plus c2 x2 is equal to 1. How about that? And both c1 and c2 are equal to 0. Then we have 0x1 plus 0x2 is equal to 1. And now that's a valid single equation in two variables, but it's not consistent because we have 0 equals 1. So that is also not true. What about 3? A homogeneous linear system of m equations in n variables always has infinitely many solutions. So we can come up here and take a look. M equations, n variables like that. So always has infinitely many solutions. What that really should mean to you is that ax equals 0 has infinitely many solutions, which means that the matrix does not have a pivot position for every column. But the thing is, with an m by n matrix, we could have n pivot positions because n is less than m, so we will still have some rows down here that don't have pivots, but we can definitely fill up all of our columns with pivots. Thus, we could have a homogeneous linear system of m equations and n variables without infinitely many solutions. We could only have the trivial solution. That said, if we have an n by m system of equations, you kind of see no matter what we do, we can't fit m pivots into here because we only have n rows worth of pivots to work with, and n is less than m. So therefore, the null space will be non-zero dimensional, and thus it will have infinitely many solutions. So 4 only is our answer for number 1. Let's consider this linear system of equations. Under which condition will the system be consistent? Let's make this into a matrix. We have 2, 1, negative 1, A, 1, negative 1, 2, 1, 4, negative 1, 3, A squared. I'm going to copy this over, and then what we're going for here is to have two individual rows be equal to the same thing on the left side, and then have some functions of a and constants over here on the right side that we know have to be equal in order for the system to be consistent, so we can set those two terms equal to each other and solve for a. So let's see what we can what we can do with that. Let's subtract, I'll move this out too. Let's subtract 2 row 1s from row 3. That gives us a 0, -3, 5, and -2a there. Now what? That didn't particularly help us out. That might have just been a waste. Let's subtract 2 row 2s from row 1. We will get 0, 3, -4, so -5. And what do we say? We're subtracting 2. Yeah, so -5, a -2. Okay, well there's something right there. If we switch the signs on that row right there, we see that we have 0, 3, -5, and in order for the system to be consistent, these two have to be equal to the same value on the right side. So we can say that a minus 2 is equal to -a squared plus 2a, otherwise known as a squared minus a minus 2 is equal to 0, a minus 1, no, I'm bad at this, a minus 2, a plus 1. There we go. So a is equal to 2 and -1 will make the system consistent, so D is our answer for 2. 3. A and B are two 4x4 matrices. Which of the following is always true? They love, I'm skipping around here, but they love putting answer choice D in this exact type of problem. The only way that we can take this equation here and say that B is equal to C is if we know that A is invertible, so that we can multiply the left by A inverse, the right by A inverse, so that A inverse A will just turn into the identity matrix. But since we don't know if A is invertible, this can't be true. What about B? Yeah, I really am skipping around. If AB is symmetric, then BA is also symmetric. Well, this is in the same camp of A, which is if A plus B is singular, then either A or B is singular. The camp of just these kind of really iffy, yeah, I'm not sure, that sounds like it could be true, answer choices that they love putting on these questions. And at least what I do, if I see that kind of thing, is, I keep it in the back of my mind, but there's probably an answer choice that is much more obviously true or false, and you can just answer that one and be sure that the other ones are wrong because you're so sure that the one that you found is right is right. It's where you get into the 1, and 2, that kind of thing, the multiple choice ones. You know what I mean? Where it gets hairy. But let's look at C. If A and B are similar matrices, then the determinant of A is equal to the determinant of B. So let's make an analogy to diagonalization, or just use diagonalization to show why this is true. So two similar matrices are only similar if there's some invertible matrix P such that you can write A equal to P, B, P inverse. And we know that the determinant of this matrix here is the same as the determinant of the diagonal matrix B over here. And as a result, A and B, we know they're similar matrices because we were able to do this, and we know one of the properties of this kind of diagonalization is that the determinant of this guy is equal to the determinant of that guy. So this, from other bits of the curriculum, we know that this is true. E, if AX equals B is consistent for some B not equal to 0, then A is non-singular. Well, that's not necessarily true, because let's think about a transformation that takes in all of R3 and spits out a plane in R2. So we've gone from R3 to a plane in R2, so you can think about think about the number of pivots that our transformation matrix must have. It has to have 2 pivots because we are spanning 2 dimensions of our output space, and as a result, the null space must be 1-dimensional. You can picture the whole line of vectors normal to that plane getting squished onto that single point of the plane as you take in all of R3 and transform that into the 2-dimensional plane. So no, not necessarily. Just because we are consistent for some vectors that are not the origin, it doesn't mean that A has an inverse. So E is incorrect, and these two are just incorrect. You can test them out, and you'll be able to find cases where they're not true. I'm not going to go do that. I don't really feel like it, because we know that C is a true statement. 4, we have a 4x4 matrix A that's row equivalent to B. Which of the following statements is true? A, well, if we look at B, B is in the reduced row echelon form. We see this stair-step pattern here with our leading terms, and all of our leading terms are 1s, and all of the areas above our leading terms are 0s. So row echelon form, that's confirmed, so A is false. The determinant of A is not 0. Well, our matrix is upper triangular, which means that the determinant is just the product of this main diagonal here, where in this case that is 0. So no, B is not true. The null space of A has dimension 3. Well, the null space is going to be the number of columns equal to the number of columns minus the number of pivots. So in this case, the null space will have a dimension of 1 because we have 3 pivots and 4 columns, so C is not true. What about D? The column space has a dimension of 2. Well, no, because the dimension of the column space is going to be equal to the number of pivots. We have 3, so the dimension of the column space will be 3. If AX equals B is consistent for some B not equal to 0, then it has infinitely many solutions. Oh, look at that. That's a callback to what we were talking about right up here, because we can use that same analogy. So let's see. We have this matrix up here, which goes from R4 to R4, but it takes in all of R4, but only outputs 3 dimensions worth of R4. So there must be an infinite, and this is impossible for us to conceptualize, but an infinite number of 3D spaces that all got squished onto the 3D space that we're getting as an output. So you could also, and I could have just explained that much better, because our null space is non-zero, and as a result, we should have infinite solutions. But that's only for the origin. Yeah, what I said before was better. So you have this transformation from all of R4. It's losing a dimension, so we're going down to a three-dimensional shape in R4, but because we're going down a dimension, there should be an infinite number of vectors that have to get squished onto every point in the R3 space that you get in the end. Okay, I'm sorry. It's weird to conceptualize. Hopefully that made vaguely some sense. So 4 is E. 5, let's consider this linear system. For which value of A does the system have an infinite number of solutions? So we're looking to set this up and find a free variable. So 1, 1, 3, 3, 0, 1, A, -1, 2, 3, A squared, A plus 2. Let's reduce away, but I'll need I will need a duplicate. Okay, let's subtract 2 row 1s from row 3. That will give us 0, 1, -6, and -4 here. Let's Let's subtract row 2 from row 3. Subtract row 2 from row 3. That will give us a 0 here, a minus 6 minus a here, and plus 1, so a minus 3 there. In order for us to have infinitely many solutions, we don't want our system to be inconsistent, but we want this entire bottom row to be equal to 0. And as a result, a squared minus 6a must be equal to 0, but also a minus 3 must be equal to 0. So up here we'll get two roots. A is equal to 0 and 3, but here we only get a is equal to 3. So the only value of a for which both of these entries is 0 is a equals 3. So 5 is D. 6. If the determinant of this matrix is 6, we're finding the determinant of this other matrix. So we can start crossing off the changes that they've made here as long as we adjust this determinant of 6 as we go, and we should be able to make our way slowly from this matrix to this one. And I'll zoom in and move this out of the way a little bit. Okay. So what have they done here? They've multiplied this row by 2, this row by 3, sorry, those are columns, not rows, and this row by 1/6. So multiplied a row by 2, multiplied a row by 3, no, those are columns, yet again, sorry, and multiplied a row by 1/6. And we know that whenever we multiply a row or a column by a factor, we have to multiply our determinant by that factor. So if we undo all of those changes, we'll actually have to do the opposite of what I just described here. We'll need to divide by 2, which gets rid of this, and we have a 1/6 here. We need to divide by 3, and then we need to multiply this row by 6 to get rid of those 1/6. There we go. But you'll notice that that was kind of useless because all of this is just 1, so we can get rid of that. Okay, what else do we have to do? It looks like they've taken the transpose of the matrix, but we're also going to have to switch the A and the B column. And that's legal to do because even though we can't, in normal matrix operation terms, like elementary row operations kind of stuff, we can't switch columns, but what we can do is take the transpose of our matrix, which doesn't change the determinant, switch two rows corresponding to the two columns we wanted to switch, and then take our transpose back. And so our determinant will not have been changed by any of the transposes, but it will be multiplied by -1 for switching two rows. So switching these two will multiply our determinant not by -6, but by -1. And then you'll see since we have we have now a C column, a B column, and an A column. All we need to do is switch the A and the C column, which is another -1, so we're left with A, B, C, but we want A as a row, B as a row, C as a row. So we take our transpose, we're left with A column, A row, B row, C row, and that transpose does nothing. Overall, we did nothing. This was useless, and our answer is still 6 for A. I think the 2 times they've done that, where the determinant has just been equal to the one that they gave you to begin with, both times the value you got was the same as the question number. I'm not sure if someone thought that was funny or what. Okay, question number 7. These determinants are actually some of the easiest to take, which is nice. None of the determinants that they make us do are actually ever that bad. And I'll show you why. We know that we can take this determinant and look for any elements that are in a row by themselves, or a column. So in this case, this 1 is in a row by itself. So what we'll need to do is pull it out and multiply it by the determinant that we get by crossing out the row and the column that that 1 is in. But more importantly, we need to remember that there's this scheme of signs that will go along with any terms that we pull out. So it goes plus, minus, plus, minus, minus, plus, minus, plus, plus, minus, plus, minus, blah, blah, blah. It's that kind of thing. I'm not writing out the whole thing. So what I do is just, I'll kind of zoom in to show this. I count over to the term that we want to pull out. So this 0 is a plus, this 1's a minus, plus, minus, plus. So we can take that 1 out with a plus and multiply it by this matrix 0, 3, 0, 0, 1, 2, 2, 3, 3, 2, 2, 4, 0, 3, 0, 5, taking all of the terms that don't share a row or column with that 1. Now you'll see that there's a 3 in a row by itself, so plus minus, we can take out a negative 3 and multiply by the determinant of this matrix. So now we have 1 times 3 multiplied by this 3 by 3 determinant, 1, 2, 3, 3, 2, 4, 0, 0, 5. Oh, look at that. Plus, minus, plus, minus, plus. We can pull out that 5 with a plus sign on it and set this equal to 1 times 3 times 5 times this determinant here, which will be what? Negative 4. And there we go. We get in the end. Oh, yeah. See, but here's where these questions get you. Remember when I said that we were pulling out a negative 3, and then I just wrote a 3? Yep, that's what'll happen to you. That's how you lose points right there. But our answer is positive 60 because we get negative 4 times that negative 1 that I almost missed there, and we get 60. So 7 is A. Close one. Okay, 8. If A is given here, then what is the 2-1 entry of A inverse? So we will need the determinant of A, which we can take as plus, minus, plus. So plus sign multiplied by 4 because it's in a row by itself, multiplied by the determinant of the matrix formed by crossing out the row and the column that 4 is in. That's a negative 1. So our determinant is 1 or negative 1 over, sorry, I need to be more specific, don't I? Any individual element of our inverse will be multiplied by 1 over our determinant, so 1 over negative 4. Now to find the 2-1 entry of A inverse, what we're going to be doing, the 2-1 entry is here, we will be finding the 1, 2 cofactor for this position right here. That's the 1, 2 position of our matrix. The cofactor there is just whatever sign that position has in our whole plus, minus, plus scheme. So that's a minus sign times the matrix formed by crossing out the row and the column that 0 is in. So we get 1, 1, 0, 1. That's negative 1. Well, this whole thing is negative 1. And so we get positive 1/4, which is B for 8. 9. Let's consider the vector space P2 of all polynomials of degree at most 2. Let's find all real numbers A such that t squared minus at plus 1 minus a squared is in the span of these 3 other vectors. So I'll be making an augmented matrix with expressions of these vectors in these terms. So we'll have a t squared component, a t component, and a constant component. So this vector, for example, would become 1, negative 2, 1. So making our augmented matrix, we will have 1, negative 2, 1, 0, 1, negative 1, 3, negative 2, negative 1, and then we're finding the values of A such that 1, minus a, 1 minus a squared is in our span. So we need not only for, well, yeah, we need our system to be consistent, which means when we reduce this, we should get 3 pivots. Let's subtract row 1 from row 3. That gives us 0 here, -4 here, and gets rid of that. Let's add two row 1s to row 2. That gives us a 0 here, a 4 here, and a +2 there. Let's flip the sign of this bottom row, and we already have 2 pivots, but in order for us to have a third, in order for us to have a third, oh, look, we are not going to have a third. Okay, that's interesting. I'm slightly wrong here. So really it seems like what we need to do is make sure that this system is consistent, because if this term doesn't equal this term over here, then we can use row 2, we can subtract row 2 from row 3, and we will get 0, 0, 0 equals something that's not 0. So that's inconsistent and no good. Okay, so solving this here, we see that a squared must be equal to -a minus 2, so a squared plus a minus 2 must be equal to 0. A plus 2, a minus 1 must be equal to 0, so a is equal to 1 and -2. So the misconception I had to begin with was that these three, not that one, these three polynomials spanned, P2, but in fact they do not. But that doesn't mean that this third polynomial, or this fourth polynomial that we're checking, can't be in the span. And it turns out it's in the span for a is equal to -2 and 1, so 9 is D. And I made this way too small to, 9 is D. 10. Let's consider this linear system that someone thought was extremely funny to put in there, but we're very serious. We're very serious here, so that's nothing. Suppose that this is a set of solutions to. Suppose that the solution set of this system is a linear subspace of R3. Which of the following conditions must hold? So this is another one of those cases where it's a little. A lot of these answer choices are a little iffy, and you're like, okay, that could be true. Maybe A has to be equal to B. Maybe A doesn't have to be equal to 0. It's really unclear. But what we do know for certain is 2 important facts. One, the null space is a subspace of R to the n, where n is the number of columns of our matrix. So that checks out right here. We have 3 columns. We're looking for a subspace of R3, and the null space by definition is a solution to AX equals 0. So if B over here is equal to 0, we have exactly the null space. So 10 is E, and this is one of the ones where it's more difficult to show why all of these other ones are false than why this particular one is true. Okay, 11. Determine all the values of C such that the following vectors form a basis of R3. So here's a case where when we put them together and row reduce them, we want to get 3 pivot positions. -1, 0, 1, 4, 2, 4, 2, 1, C is what we're dealing with. Let's add row 1 to row 3, 0, 8, C plus 2. And let's divide row 3 by 4. No, sorry. Yes, by 4. We get 2 and C plus 2 over 4. And in order for us to have 3 pivots, let's subtract row 2 from row 3. We get 0 and -1 here. this guy needs to not be equal to 0. And this is equal to 0 when c plus 2 over 4 minus 1 is equal to 0, or c plus 2 over 4 is equal to 1, or c plus 2 is equal to 4, or c is equal to 2. So, but that's the situation we don't want. We don't want that, because then we'll have a 0, 0, 0 on the bottom. So really our answer is c is not equal to 2. So 11 is E. Let's determine the rank of this matrix. That will just be the number of pivot positions in our reduced, well, we don't even have to find the reduced echelon form, just the echelon form. 1, negative 1, 3, 2, 4, 7, 2, 1, negative 1, negative 10, 7, 5. Let's subtract, but first I gotta duplicate, and let's make sure I wrote down all the right. Yeah, I did. Okay. Let's add row 1 to row 3. 0, negative 11, 10, 7. Let's subtract 4 row 1s from row 2. 0, 11, minus 4, so minus 12 is negative 10, and minus 8, so negative 7. Well, look at that. Let's multiply this row by negative 1 and subtract it from row 3. We get 0, 0, 0. Pivot position, pivot position. Our rank is 2. 12 is C. Suppose that W consists of all vectors such that x plus 3y minus 2z is equal to 0. Which of the following forms a basis for the orthogonal complement of W? So this one is very easy if you remember anything from Calc 3, because we know that a plane is defined by its normal vector, which is the vector that forms a 90-degree angle with that plane, so it's orthogonal to the plane. So the basis vector, the basis for all vectors that are orthogonal to that plane right there, is just the normal vector, which is formed from the coefficients on x, y, and z, so 1, 3, negative 2, and it really is that easy for 13, that's B. What about 14? Suppose that W consists of all vectors such that, okay, they're giving us the exact same point, or the exact same plane. We're finding the distance from that point to that plane. So this gets a little hairy with the stuff that we learned in this class. I'm sure you can figure out the orthogonal projection, etc., that you need to figure this one out. But there's actually a special formula for this that we can use regardless. If we call the terms on A, B, and C, or sorry, on x, y, and z, if we call those A, B, and C, so A equals 1, B equals 3, C equals negative 2, and we call these points x1 equals 1, y1 equals 2, z1 equals 0, we can find this distance pretty easily as the dot product between the vector x1, y1, z1 and a, b, c. So that's 1 plus 6, we get 7, and then we just have to divide that by the magnitude of this ABC vector. So that will be 9, 10, 14, root 14 down there. And careful, you might be a little worried at this point, as was I. I wasted way too much time getting 7 over root 14 and looking at the answer choices and getting unhappy. But multiply both sides by root 14. We get 7 root 14 over 14, or just root 14 over 2. So 14 is A. We have an inconsistent linear system here. Let's find the least squares solution. That means we are solving A transpose AX is equal to A transpose B. Let's do that. A transpose is 1, 1, 1, negative 2, 0, 2. we're multiplying that by 1, 1, 1, negative 2, 0, 2, and we'll get a 2 by 2 matrix with entries 3, 0, 0, because it's symmetric, we can just fill that in, and 8. Okay, A transpose B, on the other hand, is 1, 1, 1, negative 2, 0, 2, multiplied by B, 1, 2, 4. That gives us a 2 by 1 matrix with entries 7 and negative 2 plus 8, so 6. Let's solve this system here, and really we're solving the augmented system 3, 0, 7, 0, 8, 6. So x1 is equal to 7 over 3, x2 is equal to 3 over 4. And that is our solution. That is our least square solution. So 15 is D. (16) Let V be a subset. I'm pretty sure that's what that symbol is, of R2, and it's the set of vectors xy with x times y greater than or equal to 0. Which of the following statements is true? Let's plot this out graphically with all of the subspaces of Rn. It's usually easier to think about them graphically, whereas subspaces of Pn, you really have to test all the properties by hand. So we know that x times y is greater than or equal to 0, and as a result, either both x and y have to be positive or they both have to be negative. So we are dealing with the coordinate axes and these two quadrants 1 and 3. But you'll see pretty quickly, if we take, for example, this vector and this vector, if this is a subspace, when we add them together, we should get another vector that's in the subset, but we add these together and we get a vector that is most definitely not in our set to begin with. So it is not a subspace because it's not closed under vector addition. It does contain the 0 vector, and it does stay closed under scalar multiplication. You know, this quadrant extends infinitely this way, so if you choose any of these vectors and multiply them by any factor, you'll still be good no matter how far you go out. So 16 is C. 17, let A be an m by n matrix if W is the column space of A transpose. Let's not think about that. Let's think about the row space of A, because that's the column space of A transpose. Then the orthogonal complement of W is what? This is just something that you have to remember. The null space is orthogonal to the row space. I don't know. I should have like a mnemonic for that or something. Null space orthogonal to row space. Nah. You can come up with something obscene for NOR if you really want to remember that. But the null space is orthogonal to the row space, so the null space of A is the orthogonal complement to the row space, also known as the column space of A transpose. So 17 comes out to A. Here is 18. Let's find the 3,2 cofactor of A. Well, the 3,2 cofactor is going to be the sign of this position in the matrix, which is plus, minus, plus, minus. So we use a negative sign outside of everything, and then we're multiplying by the determinant of the matrix formed by crossing out the row and the column that 2 is in. Since we are left with 1, 3, 0, 2, negative 4, negative 1, 0, negative 1, 0, we can do a couple of things. There we go. We can pull out this negative 1 because it's in a row by itself, and noting that it has a plus, minus sign on it, so we're pulling out negative 1, or just positive 1. So multiplying that by this negative 1 out here, we still have -1 multiplied by the determinant of the matrix formed by crossing out that row and column. So we have 1, 2, 0, -1. That gives us, that evaluates out to 1. So D should be our answer for 18. And it is. 19. Let P4 be the space of all polynomials of degree at most 4. The subspace V of P4 contains all polynomials such that P0 is equal to 2P1. What is the dimension of V? So I will give you an explanation for this, which I think makes a whole lot of sense. The thing is, it directly conflicts with the example that I gave for a similar question to this. It was a subspace of P3, and the condition was P at 0 is equal to P at 1. And you'll see why these conflict in just a second. So the generalized form of a polynomial in P4 is P of t is equal to C1 plus C2t plus C3t squared plus C4t cubed plus C5 t to the fourth. If we evaluate P at 0, we get C1, and P at 1 is C1 plus C2 plus C3 plus C4 plus C5, except that we're finding, we're getting 2P1 because P0 is equal to 2P1. We'll need to equate these two. So we'll multiply this by 2. Setting them equal to each other, we see that 0 is equal to 1 C1 plus 2 C2 plus 2 C3 plus 2 C4 plus 2 C5. Now, if you want to think about how many dimensions this kind of equation takes up, I like to think about a plane. So a plane in 3 dimensions is defined by C1x plus C2y plus C3z, and let's just set that equal to 0 for now. So even though there are 3 variables that you can play around with and slide up and down, they all have to, moving 2 of them at once, you can only really move 2 of them freely. The other one has to compensate for the changes made by the other 2. So in the end, there are 2 free variables here, and as a result, a plane is 2-dimensional, even though it includes 3 variables. So likewise, this over here includes 5 variables, but since we can only mess around with 4 of them, and the 5th one, or it can be any of them, but one of them has to compensate for all of the stuff done by the other 4 in order for it to still be equal to 0, this is a 4-dimensional subspace. There we go. But just showing you why this doesn't mesh with my explanation for this thing right here. P at 0 is C1, P at 1 is C1 plus C2 plus C3 plus C4. And so subtracting, we get 0 is equal to C2 plus C3 plus C4. And by my explanation that I made here, we would guess that to be a 2-dimensional subspace, except it's not. It is not at all. It is a 3-dimensional subspace. The thing is, oh, I think I actually get it. Sweet. I love it when this happens. Okay, so sure, this is a plane with, well, okay, it's in the form kind of a plane, but there's this variable still exists. We can still mess around with C1 all we want. C1 is the only truly free variable here. These 2 can be free, while this one kind of does all the work to fix the stuff that they get up to. But C1 is still there. Okay, so this makes sense. Okay, we have 4 variables here, but only 3 degrees of freedom. Okay, got it. Makes sense. Hopefully that makes a little bit more sense to you too. So 19 is C. Cool. I came into this not thinking I would be able to figure that one out. Okay, here is A. Let's find the values for C such that the system AX equals 0 has a non-trivial solution. That should directly translate in your head to the system. The system does not have 3 pivot positions, aka the rank is less than the number of columns, aka the dimension of the null space is greater than 0. We can see one of these values right off the bat. If C is equal to -1, we can add row 1 to row 2 and subtract row 1 from row 2 and set that entire row equal to 0. So C is equal to -1 is definitely one of our choices there. But now we're going to actually reduce this matrix a little bit, 1, -3, C, to see what else is going on here. Okay, let's subtract row 1 from row 3. We get 0, -2, C minus 2. Let's subtract row 1 from row 2, 0, C plus 1, 0, and there's our other solution. This whole step was completely useless. We see that if C is equal to -1, oh wait, that's the one we already found. That's the solution we already know about. So that's just showing you kind of what we were talking about there. Yeah, so -1, still very much a solution there. Okay, great. Let's now subtract. No, that won't work. That won't work at all. Let's just go for something. Let's divide this by 2. There we go, and subtract row 3 from row 1. We get 0, 2 minus C over 2 minus 1, so 1 minus C over 2. That doesn't really help with anything at all. I think, okay, I actually think I get it. So what happens if this position is equal to 0? If this position is equal to 0, we just have 2 constants here, so by definition we can use one of them to set the other one equal to 0. So we should be able to take this thing here, C minus 2 over 2 equals 0, and solve it. Solving this, we get 0, and C is equal to 2 there. So there we go. Yeah, if this is equal to 0, I'll just show you, no matter what C is, there is some multiple of -1 that we can use to set that position equal to 0. Thus, we'll only have 2, what do they call it, pivot positions. So E is our answer for 20. Let's find a non-singular matrix P such that P inverse times this matrix times P is equal to this guy. So this is just a kind of mixed up diagonalization expression here where we're looking for P, which will be composed of the eigenvector, the first eigenvector related to lambda equals 1, the second eigenvector for lambda equals 1, and the third eigenvector for lambda equals 6. So at this point, we can write a minus lambda I for lambda equal to 1, and we should be able to solve for 2 different eigenvectors. 1, -2, 1, -1, 2, -1, 2, -4, 2, -4, and 2. Let's divide row 3 by 2. We get 1, -2, 1, and we can use row 1 to set both of these rows to 0. Seeing that this says x1 is equal to 2x2 minus x3, we can make a vector out of these 2 free variables. x2 is equal to, 2x2 is equal to x1, I should phrase it that way. 2x2 is equal to 1x2, and it's equal to 0x3. Then we'll get an x3 vector. X1 is equal to -1 x3, 0 x2, and 1 of itself. So these are our two eigenvectors there. And looking at our answer choices, every single option here agrees with us. So we should be on the right track so far. Let's plug in lambda equals 6 and solve for our final eigenvector. -4, -2, 1, -1, -3, -1, 2, -4, -3. Okay. Let's flip all of the signs in this matrix because there are way too many negatives. Let's add two row 2's to row 3. That gives us a 0 here, a 10 here, and a 5 here, so we can turn this into a 2, 1. Let's subtract two row 3's from row 2. That gives us, oh no, I don't really want to do that at all. In fact, let's subtract row 3 from row 1, 0, -2, so this becomes 1 and, no, wait, gotta be careful. It becomes 2 and -1, like that, or I'll just leave it as 2 for now. Yeah, we're gonna get fractions, so might as well embrace them. Let's subtract row 1 from row 2. That gives us a 0 here and a 3/2 here, dividing, okay, no, we're fine. Sorry. No, we're not fine. We're not fine at all. So reducing this, I'll flip all of the signs in this matrix because there are way too many negative signs running around. And what can we do? Let's subtract 4 row 2's from row 1. That gives us 0 minus 12 is -10, minus 4 is -5, so this becomes 2, 1. Let's add 2 row 2's to row 3. That makes a 0 here, a 10 here, and a 5 here, so that's another 2, 1, which we can use row 1 to set to 0, 0. Set that to 0, 0, and then we can actually go and solve because we see that we have two equations. X1 is equal to -3 x2, -3 x2 minus 1, and I'll just do that really quickly. No, what am I saying minus 1? Minus x3, and x2 is equal to -1/2 x3. So if we're making a vector out of x3, oh wait, I'm not done. What am I doing? What am I doing? We need to rearrange this so I can actually see what I'm doing here, because this is not in reduced form. Let's subtract 3 row 2's from row 1. That gives us a 0 here. Minus 3 over 2 is -1/2. So we can say that x1 is equal to 1/2 x3, and x2 is equal to -1/2 x3. So we can make an eigenvector 1/2, -1/2, 1, otherwise known as 1, -1, 2, just to make our lives a little bit easier. And that third vector only appears in option A, so 21 is A. 22, here is a new A. Let's find the eigenvalues of A. We will be solving A minus lambda I, so I'll plug all those in, and since 1 minus lambda is in a row by itself, we can bring it out with a plus sign, 1 minus lambda, and multiply it by the determinant of the matrix that we get by crossing out its row and column, which is this guy right here. the determinant of that will be 2 minus lambda times 8 minus lambda plus 5 is equal to 0. There we go. So we know that when lambda is equal to 1, this whole side is definitely equal to 0. So lambda is equal to 1 is one of our eigenvalues. So we agree with all three of these. Then if we refactor this inner portion, one mistake you can make here is trying to refactor everything, like expanding all of this into a big trinomial, but we actually don't need to do that at all. We can just go in here and say that lambda squared minus 10 lambda plus 16 plus 5 is plus 21 is equal to 0. Lambda minus 7, lambda minus 3 is equal to 0. So lambda is equal to 3 and 7 are also solutions. So 22 is B. Which of the following matrices is not diagonalizable? So some things that we know: any upper triangular matrix with n distinct values along its its main diagonal is automatically diagonalizable. And so we can apply that to matrix E here. It has 5, 0, 7 as values along its main diagonal. Those are in fact its eigenvalues, and because an n by n matrix with n distinct eigenvalues is always diagonalizable, E is definitely diagonalizable. Additionally, if a matrix is symmetric, it is always diagonalizable. So D, because the three values off main diagonal are equal to its mirror image across that main diagonal. Main diagonal, D is also diagonalizable. Additionally, looking around here, you can go prove for yourself that these two are diagonalizable, but I will not, because if we were taking this in an exam, I would hope we would try to test option A first. And alarm bells should already be going off, seeing that we have a eigenvalue with a multiplicity of 2 here, because these elements along the main diagonal, if we have an upper triangular matrix, which we do here, are the eigenvalues. So we have lambda equals 0 with a multiplicity of 2, and lambda equals 3. So in order to be diagonalizable, we need 3 eigenvectors. And each of these eigenspaces can have either one eigenvector or potentially 2 eigenvectors in the case of this multiple eigenvalue. But we know just by looking at A that when we plug in lambda equals 0, this is the same as lambda a minus 0I, plugging in lambda equals 0, and we see that this has 2 pivot positions, and as a result we'll only have one free variable, so we can only have one eigenvector. So with 2 total eigenvectors, we cannot span R3 with our eigenvectors, so A is not diagonalizable. So 23 is A. 24. Which statements about symmetric matrices with real entries is or are true? Every symmetric matrix is non-singular. No. Look at this. 0, 0, 0, 0. That's a pretty singular matrix, looking like a pretty singular matrix to me. Its determinant is 0, so this is not true. What about 2? All of the eigenvalues of each symmetric matrix are real numbers. Also no. What about 0, 0, 1, 1, 1? No, wait. Interesting. Oh, okay. I remember from the, what's it called? The spectral theorem, the spectral theorem of symmetric matrices from section, I think 7.1 or 6.7, right near the end there, says that 1, matrices that are symmetric are always orthogonally diagonalizable, and one of its other points is that they always have n real eigenvalues. And so, yeah, this should be true, although I'm not exactly sure how to directly prove it. Okay, what about 3? There exists a symmetric matrix which is not diagonalizable. Well, going right back to that spectral theorem I was talking about, that tells us that all symmetric matrices are diagonalizable. What about 4? Symmetric matrices are diagonalizable. Yep. Yep, I agree with that. I kind of wish there was an option here that had 3 and 4 as answer choices, but sadly there is not. So 2 and 4, by that same theorem, which you should go take a look at, because usually there's 1 or 2 questions which directly reference it, as a good thing to know. That should be our answer. So E for 24. Yep. And finally, easy peasy, we can do this one. Okay, we're solving this. We're not even using an initial condition. That's great. So we're solving a minus lambda I. The determinant of a minus lambda I equals 0, actually. So 3 minus lambda times 3 minus lambda minus 4 is equal to 0. Lambda squared minus 6 lambda plus 9 minus 4 is plus 5 is equal to 0. Lambda minus 5, lambda minus 1 is equal to 0. So lambda is equal to 5 and 1. For lambda is equal to 5, a minus lambda I will become negative 2, 2, 2, negative 2, which simplifies down to 1, negative 1, 0, 0, and we'll get an eigenvector of 1, 1 out of that. So this guy, for lambda equals 5, we get that eigenvalue pair. For lambda equals 1, a minus lambda I becomes 2, 2, 2, 2, simplifying down to 1, 1, 0, 0. And so we get an eigenvalue for lambda equals 1 of negative 1, 1. And since all we're doing here is setting up our solution, which is in the form C1 V1 e to the lambda 1t plus C2 V2 e to the lambda 2t, we should get C. And you'll see what they tried to do here. We got an eigenvector of negative 1, 1, but they have 1, negative 1 in here. That's perfectly legal because this B can be any real number, so that can be negative to compensate for the negative 1 that they've pulled out from there. But overall, we have e to the lambda 1t, e to the lambda 2t, multiplied by both constants and both eigenvectors. So 25 is C, and we are out of here.